Hi, I'm Seongsik, the presenter of this study on numerical evaluation of eDNA method to quantify fish population. First, introduction. Necessity of fish abundance monitoring. Since 1970s, the sustainable fish stock has gradually decreased due to the population growth and overfishing. So the fish abundance monitoring should be proceed for management of marine resource and sustainable use of them. The Commission way to estimate a fish abundance, specifically its severity to visually dependent way and visually independent way. The visually dependent way means the statistical method based on a catch. It has some error for from gear selectivity because each gear has own gear's shape and length and other characteristics. And in visually independent way is surveyed for specific purpose. So it has relatively low error. However, it requires high costs such as expensive equipment and manpower and time and others. A various study on eDNA and aquatic organisms has conducted, such as biodiversity and detection and abundance estimation. Specifically, the environmental DNA, defined as collected DNA from a variety of environmental samples. The studies on estimation of fish abundance using the eDNA have shown a feasibility. It shows cost-effective result because it needed water sample only, and various studies on eDNA have been proceeded. And some studies proposed to estimate the abundance and distribution of jack mackerel using eDNA. And the paper shows the high performance to estimate the abundance, but was not able to estimate the spatial distribution. And the author mentioned the cost was insufficient sample relative to the study area. So we did numerical evaluation study to evaluate the eDNA proposed based on case study as the number of eDNA samples to figure out the three things. First, the insufficient eDNA sample caused the failure of distribution estimation. And second, so how many samples are needed to reasonably estimate the fish distribution? Also, how the estimation accuracy varies according to the number of samples. So, and this is approach of the eDNA approach. There are two inferences. The first, the forward inference to calculate the eDNA concentration, and backward inference to estimate the fish density from eDNA concentration. And in the tracer model, we can calculate the matrix A, design matrix, and we can calculate the eDNA concentration using this matrix A. And in the matrix A has n by m size. The m is the number of aquatic cell, and the case column is the eDNA concentration output from the tracer model if the fish density of case cell set to be unit value such as 1 individual per meter cubic, and all other cells have null fish density. So specifically, one of column of matrix A is obtained by a single run of tracer model. Example, set unit fish density in grid number 1 and 0 fish density in the other grids, and run the tracer model, and we can get the one of column number 1 is obtained. And second, if matrix A is obtained by running of tracer model m times, eDNA concentration can be calculated without the tracer model anymore. And the vector x, the fish density vector, can be estimated by Bayes and linear regression using matrix A and vector y. However, in this case, we needed to simplify because of computational cost, so we interpolated vector y and then estimated vector x by multiplying inverse A matrix by y as follows this equation. The flowchart of numerical evaluation, we first randomized 15 cases of latent fish density and calculate the A matrix and calculate the eDNA concentration. And we divide the section in the study area and then to pick the eDNA concentration in each section according to top and bottom cable condition, known value ratio. And then interpolate the picked eDNA concentration to the whole cells and estimate the pitch density x vector x by multiply A inverse by y, and then eliminate the outlier among the estimate x vector and validate the estimate vector x and with latent x. And we randomized 3 cases of related pitch distribution. Case 1, all randomizing from 0 to 10 individual meter cubics of pitch density. And case 2, a pitch school located at specific point of surface. The pitch school has pitch density from 10 to 15 individual meter cubic. And case 3, a pitch school located in specific bottom point. And we also considered 5 sub-cases of each case 1 to 3. So totally 15 cases of latent pitch density was made by randomizing. And we considered cable condition from 1 to 90%, top and bottom, both of them. We validate the pitch abundance by using reproducibility following this equation. If the reproducibility is over 1, it means overestimation. If it greater than 1, it means underestimation. And we validate the pitch distribution estimates by correlation coefficient and check whether the pitch score is materialized or not by visual inspection and histogram graph and scatter plot of pitch densities. And next, the result of case study as related pitch distribution. The reproducibility of abundance estimate and the correlation coefficient between rated and estimated pitch densities. First, the reproducibility of abundance. The difference of reproducibilities was up to 0.12 and 0.229 at the top and bottom 1% cable respectively. It is expected that the reproducibility of estimated pitch abundance may vary depending on the pitch distribution if the eDNA sample is insufficient. And there is no difference of reproducibility as pitch distribution if there aren't enough eDNA samples, and R between latent and estimated pitch density. The R value shows a range of 0.07 to 0.11 and 0.39 to 0.98 and 0.82 to 0.86. At top 1%, 50%, and 90% cable respectively. There was no significant difference between R values according to pitch distribution. Next, we show the case study as cable condition. The reproducibility of abundance. The top cable condition showing the reproducibility close to the rated was 3% for case 1, 1 and case 2 1 and 90% for case 3 1. And all estimates was underestimated. In the bottom cable condition, the 90% of cable shows reproducibility close to the latent for all cases. And the approach shows high reproducibility over 0.8 regardless of the number of samples. And in the result of correlation coefficient, in case 2-1, the R value at top 1% cable was 0.1, which was 0.07 higher than that at bottom 1% cable. It depended on whether the pitch score was materialized or not. The eDNA copies shared from pitch score are more likely to be selected in the top cable than bottom cable condition. And the R values increased with increasing KVR and it was 0.85 and 0.898 and 0.82 in the top 90% KVR of case 1, 2, 3 respectively. I think to obtain a correlation of over 0.6 and to materialize the pitch score, it is necessary to know 70% or more than eDNA samples relative to the study area. And next is the check result whether the fish skull was materialized or not. The materialized or fish skulls in the top and bottom K-wear condition. The top 1% K-wear of case 2-1 was partially capable of materializing a fish skull, whereas the bottom 1% K-wear was not able to do so. And these regions I mentioned, the eDNA copies shredded from a fish skull are more likely to be selected in the top K-wear than bottom K-wear condition. In the materializing comparison between the cases, case 2 and case 3, the fish skull in case 2 was reasonably materialized more than case 3. It depends on whether the fish skull is located in the surface or bottom layer of the bay. And the tidal residual current in the bottom layer of Jinhae Bay is slower than that at the surface. It means that this indicates that the transport of eDNA copies shredded from the fish skull in case 3 was slower than that in case 2, and there are more eDNA copies in case 3. The fish densities around the fish skull in case 3 were overestimated and were treated as outlier and eliminated. So the case 3 was not capable of materializing fish skull. And next, the result histogram and scatter plot. The fish density estimate under 0 individual per meter cubic. The fish density estimate under 0 individual meter cubic were set to be 0 value, and the histogram count for 0 to 0.5 in the top 1% K-area for case 2 was 3,320, higher than the 435 observed in the latent. This was because the fish densities were underestimated below 0 individual per meter cubic and were set to 0. And in top 1% K-area of case 2, the count estimated over 15, which did not exist in the latent, was 1,004. As a result, this approach may underestimate and overestimate fish density under low K-area conditions, and these issues were resolved as the K-area increased. And next, the conclusion. The case in the result of case study as rated fish densities, there were no difference of accuracy as rated fish densities. And in case study as the number of eDNA samples, it was able to estimate a fish abundance regardless of K-area condition. However, in estimation of fish distribution, it is necessary to know 70% or more than eDNA concentration relative to the study area. So this eDNA approach can reflect fish abundance, but has limitations in estimating fish distribution. Thank you.